So thank you, Chiara. Thank you, James, for giving me the opportunity to speak about this combination of a numerical and experimental approach to analyze friction in textured surfaces, lubricated contact. This work is made in collaboration with Juliette Caille-Barrios, one of my PhD, Thomas Touche, and Guidon Stakowiak in Curtin University. So first, after a short introduction, I will present you two results, one concerning the lubrication with grooved surfaces, and the second one concerning the film forming capability of dimpled surfaces. So our aim in this research is to try to design a priori some tribological surfaces in order to reduce friction or reduce wear or improve the film forming capability by manufacturing a specified morphology using, for example, a femtosecond laser. So after that, you have to characterize the surfaces, of course, their topography, but also their tribological properties. And today we focus mainly on textured surfaces, not on random rough surfaces. We know that texturing has a lot of influence on the film thickness and contact pressure, especially in AHL at the pattern scale, which means in the range of a few micrometers or less than few micrometers. And this, of course, change the contact properties that are measured at the contact scale, that can be 10 or more orders of magnitude higher, for example, when we measure the friction coefficient. And there is no systematic study of this case coupling with textured surfaces, and we'll try to study this through the Strebeck curve, which plot the friction coefficient versus the product viscosity velocity, which is in fact related to the lubricant film thickness in full film lubrication. So we'll try how it is possible to change the minimum of the Strebeck curve and to postpone it towards the low velocity and to reduce the friction coefficient by playing with surface texture. So we are in the range of lubrication in which the film thickness could be in the range of the roughness of the surfaces. And of course, we try to optimize the surface microgeometry, and we propose a strategy in which, after having measured the surface topography, we'll try to simulate the contact either in experiment, in lab experiment, or with numerical resolution here in the HL of the Reynolds equation. So the experiment is based on a classical EHL test rig, which advantage is to observe the contact continuously and to control the motion of the two solids, the ball against the disc, and then measure the friction force as well as the lubricant film thickness. So now let's see what happens with the grooved surfaces. So here we made grooves with a femtosecond laser on a ball that will roll on the disc, transparent disc we saw on the previous slide. And this texturing has a special properties because the top width is related to the depth of the groove by the relation that you see here. And there is a constant wavelength, which means that all around the ball, we have a continuously varying top width and continuously varying depth of the groove. So which means, for example, when the ball is making a round, you see here the evolution of the top width in a range of few micrometers to about 20 micrometers, and the wider top are related to shallow grooves, while the narrower tops are related to the deepest groove. So it's a specific texturing, but you will see it's interesting to see this coupling between depth and top width. So first we'll try to analyze the Strebeck curves. So you have the evolution of the friction coefficient versus the viscosity velocity product in gray, the point corresponding to the smooth ball, and in orange, the points corresponding to the grooved ball. And here we are able to analyze and to detect the AHL mixed lubrication transition for the grooved ball and the smooth ball by comparing the measured friction coefficient to the calculated viscous friction coefficient. And you see when of course, the friction deviates from the viscous contribution, the only viscous contribution, we plot here the transition between AHL and mixed lubrication. So we can also analyze the same transition by measuring the lubricant film thickness versus, once again, the velocity viscosity product. And you see here in dashed line the evolution of the film thickness with a smooth ball. And you see that for a given velocity, because you have wide tops and narrow tops, you have different level of lubricant film thickness. The round points correspond to the widest tops, and the star points correspond to the narrowest tops. And the length of the bar here gives you the minimum lubricant film thickness you have for each velocity viscosity product. And we see once again, when the minimum film thickness goes around 0, you have this transition between EHL and mixed lubrication regime. So we see that we have a good agreement in the detection of this transition, either by a measurement of film thickness or either by comparing a calculated friction coefficient to a measured friction coefficient. What happens now locally? Because I show you only average lubricant film thickness. Here we see an interferogram in which we have a groove with a wide top width, with a wide top passing through the contact. And you see that we have an increase, a local increase in the lubricant film thickness. And you see this local increase of the lubricant film thickness is entrapped between two constriction zones, which suggests that we have a very important squeeze effect. And you see this thickness is only increased locally, but we have no effect on the average lubricant film thickness, because in that case, we have a velocity viscosity product which corresponds to a mixed lubrication regime. And what we observe when we plot the lubricant film thickness for grooved surface compared to lubricant film thickness of the smooth surface, we observe two effects. For the wide top, you see that we have roughly a lubricant film thickness which is in the same range of the lubricant film thickness obtained or measured with the smooth surfaces. And you see a decrease, a steep decrease of the lubricant film thickness when the top width become lower for a critical width, which is in the range of 15 micrometers. So we'll try now to understand why we observe this phenomena. And this phenomena is also well predicted by the simulation of the lubricant film thickness. You see on this graph the evolution of the lubricant film thickness for different top width. And you see that when the groove depth is small, in the range of equal to 50 nanometers, we have no effect of the top width on the lubricant film thickness, which is not the case when the groove is deep, in which we observe this decrease of the lubricant film thickness when the top width is also decreasing. So we find by the calculation what we observe experimentally on the average, of course, lubricant film thickness. If we try to see how this average lubricant film thickness varies with the volume of the grooves, here it's a calculation, we observe we have a kind of linear evolution of the average thickness versus the volume of the groove with this coefficient delta, which represent the slope of this curve, of these dash curves. And the level, of course, of the average film thickness will depend on the friction, on the velocity viscosity product. So we try to analyze this average film thickness very simply by calculating this average over a period. And it's very easy to demonstrate that the average lubricant film thickness is equal to the central film thickness that we measure when we do the experiments in the HL test rig, plus this ratio between the deformed grooves and the amplitude of the initial groove multiplied by the volume of the groove divided by lambda. So equating to the previous equation, it is then possible to have this relationship between the central film thickness measured with a groove and the central film thickness measured with smooth surfaces. And you see here, if you want to have an increase in the lubricant film thickness, you have to make this term positive, so to play with the elastic deformation of the groove and the wavelengths of the groove. If we analyze the average contact pressure and the average lubricant film thickness, it is also possible to prove very simply why we have no evolution of the friction coefficient when we use grooved surfaces. The average shear rate is equal to the velocity divided by the average thickness using this relation. And as the lubricant film thickness with a smooth surface is quite high compared to delta V groove, we can see that the average shear rate is the same for a grooved surface as for a smooth surface. And when we calculate the evolution of the pressure profile for different top width for grooved surface, we can observe that the average pressure in grooved surface is roughly the same as the average pressure with smooth surface. So if in AHL lubrication, the viscous friction coefficient will be equivalent because the average shear rate will be the same with smooth and grooved surfaces. It is also possible to extend this approach in the case of the mixed lubrication regime. Here we plot the evolution of the friction coefficient for different experiments made with different grooved balls versus the grooved top width. And you observe this curve, which is between the level of the boundary friction and the level of the AHL friction. So we are typically in the mixed lubrication regime. So by using this very classical view of the friction coefficient with the contribution of the boundary friction and the contribution of the AHL friction, it is possible to deduce from this, calculating the AHL friction, the contact asperity ratio for the different grooved surfaces. And you see here the calculation of the contact asperity ratio that we can compare for some surfaces to the contact asperity ratio that we are able to measure by the analysis of the interferogram, experimental interferograms. So you see we have a good correlation once again between what we can calculate from the mixed lubrication regime and what we can measure in the same lubrication regime. So I go now to dimpled surfaces, which are a little bit different. So we make this cavity with a femtosecond laser. The average depth, cavity depth, is in the range of 7 micrometers. And here you see an interferogram. The lubricant enter the contact by the right side, and go outside the contact the lubricant enters the contact by the left side and go outside by the right side. And by here on this line, it is possible to measure the local evolution of the lubricant film thickness. And you see that at the rear of the cavity, you have a region of the contact in which the lubricant film thickness is increased, but around this area, you have a minimum film thickness, a lower film thickness that we call H minus. And by plotting this thinnest film thickness versus the viscosity velocity product for different slide rod ratio, we find that the transition between the mixed and HL regime is governed by the level of H minus, and when H minus goes close to zero, you have this transition, as what we observed in the case of grooved surfaces. And now we'll try to analyze what happened in this cavity. You see the cavity is not a top hat cavity. It's because of the distribution of the energy and in the laser beam. You have this kind of global shape, and you see that the cavity is also very rough. And it is possible to analyze the increase in lubricant film thickness for this cavity for different slide rod ratio. And you see that we obtain an enhancement of a local enhancement of the lubricant film thickness only when the slide rod ratio is higher than 25%. So we can try to understand what is the roughness scale, which is important in this lubricant film thickness enhancement. If we make a calculation by using the real profile of the cavity, you obtain this lubricant film thickness distribution. So a decrease in lubricant film thickness compared to the lubricant film thickness we have with the smooth surface. If you do the same with the lower envelope of the cavity, you observe we have no change of the lubricant film thickness distribution compared to the smooth surface. But when you use the upper envelope of the roughness of the cavity, you see that we have an increase in the lubricant film thickness, which is in quite good agreement with what we observe in the experiments. Once again, we can try to see the consequence on EHL friction by calculating the pressure distribution for the real profile, for the upper envelope, and for the lower envelope. And you see that the pressure is lower in the cavity and is higher in outside the cavity. So it is possible by simply saying that the load is equal to the pressure by the surface, as you have the pressure in the cavity and as you have another pressure outside the cavity. You can easily calculate the ratio between the pressure outside the cavity and the average pressure that you have in a smooth surface. And you see that it is possible to predict from this relation that you have an increase of the pressure outside the cavity. And then by you can use this pressure in order to calculate the friction coefficient with the dimple and compare it with the friction coefficient that you obtain with a smooth surface. And as the viscosity of the pressure outside the cavity is higher than the viscosity as the pressure, the average pressure you have with a smooth surface, we can deduce an increase in the friction coefficient. And that's what we observe, for example, in this plot, where we plot the friction coefficient versus the velocity viscosity product for the different characteristic profile of the cavity, the real profile, the lower envelope of the roughness, and the upper envelope of the roughness. And so we have a slight increase in the friction coefficient, which is not very important, but which is significant compared to the friction we measure with a smooth surface. So if I now go to the conclusion, we can say that the comparison between experiments and numerical simulation is very useful to define precisely the onset of mixed lubrication, the transition from EHL to mixed lubrication. We proved that concerning lubrication with the grooved surfaces, the groove wavelength and the volume of lubricant that it can carry as a first order effect on the EHL film thickness, including the effect of elastic deformation. And we can propose a criteria to give a design of groove in order to increase the lubricant film thickness with the grooved surfaces. With dimples, the film forming capability, which is, I think, something important and new, is governed by the multiscale roughness of the cavity itself. And we see that the upper envelope of the cavity profile seems to be significant in the local increase of the lubricant film thickness we observe at the rear of the cavity. And the combination between this experiment results and the numerical simulation at the relevant scales can give some keys to try to design textured surface in order to optimize lubricated contacts. But of course, as Louise said in her talk, we make only numerical simulation. It's not digital twin. So the question is for us how to go to digital twins and relevant scale in EHL or mixed lubrication. So thank you for your attention.